Good morning, good afternoon, everyone, and welcome to ARA's Webinar Wednesday. I'm Jerry DiMaggio, and again, I'll be serving as your moderator for today's webinar entitled Probabilistic Deterioration Modeling of Concrete Culverts. Next slide, please. I'd like to first go through a few housekeeping items with you. First of all, if you're experiencing an issue with regard to sound and you're using your computer speakers, please dial in using a phone. If you have another issue or continuing issue with regard to sound, please use the chat button to send a message and send the message only to the host. Please. Next slide. If you have questions, and we are encouraging you to submit questions during the entire technical program, we will address the questions at the conclusion of today's program. Send your questions and please listen carefully. Direct them to both the host and the panelists. And as I mentioned a moment ago, we'll address all questions in the Q&A period following the technical presentation. Next slide, please. To view the presentation in full screen mode, at the top of your webinar settings as shown in this slide, click on the down arrow, highlight view, and then choose fit the viewer. Just a reminder, you'll be entitled to receive 1 hour PDH certificate. However, you must attend the entire 1 hour program, including the Q&A period, to be qualified to receive this. At the end of the presentation, I'll provide more information. Next slide, please. It's my great pleasure to present, today's presenter, Dr. Ahmad Al-Hassan, who I work with very closely on a number of projects. Ahmad is a senior research engineer currently and a team leader within the Research and Technology Deployment Group at ARA. He specializes in a number of topics, including infrastructure evaluation, which we'll be hearing a bit about today, probabilistic performance modeling, risk-based transportation infrastructure management, and advanced inferential statistics related applications for infrastructure management. Dr. Al-Hassan is leading, a wide range also of pavement surface characterization projects related to both highways and airfield applications. He's also working closely with a number of his colleagues on geotechnical asset management and non-destructive evaluation, as well as performance modeling and management. Dr. Al-Hassan has authored and co-authored a large number, approximately 36, technical reports and articles related to geomaterials, transportation infrastructure, and pavement evaluation and monitoring. And now it's my great honor and pleasure to introduce my colleague and good friend, Dr. Al-Hassan. Ahmad.
Thanks a lot, Jerry, for the introduction. So today I'd like to discuss, as the title indicated, deterioration modeling for culverts. However, with more focus on the probabilistic aspect and the interpretation of these models, especially that the same modeling tools and concepts can be applied to a wide range of assets, such as bridges, with similar inspection records. The discussion will be also based on a project performed by ARA in collaboration with E.L. Robinson for Ohio DOT. Our agenda today will cover basically the culverts inspection process, the culverts performance records, and then focus more on the performance modeling and performance prediction, and have a brief discussion on alternative models and improvements to the introduced study. So first of all, in terms of culvert management, culverts in general play a critical role in transportation network. They present a safe and efficient drainage conduit to convey stream flow through roadway embankments or past some other type of flow obstructions. So the loss of culverts integrity could lead to major safety hazards, temporary roadway closure, property damage due to flooding, litigations, and considerable rehab and replacement costs. As shown here in the slide, this is not the extensive list, but in general, I would like to indicate that culvert management systems are critical in improving budget expenditures and allocation, maintenance scheduling, and prevent major failures, as mentioned earlier. Now, the main core of any management system, for that sake, is basically the inspection records that are used to assess the condition or describe the condition of the assets that are being considered. So our project was based on the culverts in the state of Ohio, and accordingly, the inspection process was performed by inspectors and engineers throughout the years, following the instructions in the Manual of Bridge Inspection by Ohio DOT. The data was, as I mentioned, provided by Ohio DOT, and the inspection process, I would like to just touch really briefly on how the inspection is done. So, for example, here's a table showing the inspection for scour, assessment for culverts specifically. As you can see in the table in here, we have to the far left 2 columns reflecting condition rating. We have a scale 1 to 4, and there have the other scale 9 to 0 or 0 to 9. They are flipped, as you can see. 1 is good, and as the number increases, it's going to a lower grade. On the other hand, on this scale, 9 is the best condition possible. The thing I wanted to point out from this table is not to go through the entire inspection process that deserves a training, not only webinar, but courses. However, what I wanted to point out is the descriptive nature or subjective nature of these descriptions. Some of these have very specific definitions, but still, the inspection process will depend also on the visual assessment that the inspector is performing. And accordingly, the definitions may differ in these conditions depending also on the surrounding environment. For example, when we talk about holes and scour holes, the definition of minor holes or large holes is somewhat relative. Even if there are definitions in the manual, there's still that inspector aspect that goes into it. Now, the inspection records that we've used in this study were provided by Ohio DOT, and they extracted all the data from the AssetWise database. As I indicated in the previous slide, there is some human subjectivity, and that does not disqualify the inspection data at all. But this is something to consider when you are performing some modeling or deterioration modeling with such data. So the table in here shows an example, actually a screenshot from that inspection data that we have received. As you can see, the records are actually compiled for the entire database for bridges and culverts into one master table. And as you can see, there's the structural number in here to the far left, changed here at the bottom, indicating that this is a new asset that we're dealing with. It can be a culvert, it can be a bridge, and there are multiple columns indicating the type of the culvert and the time also of the inspection. So this indicates the time the inspection was performed, and we had to process that data to be qualified for the analysis. Now, in our study, we have included, or we were considering 2 main types, 4-sided or box culverts and 3-sided culverts. Under these 2 main types, there were also precast culverts and cast in place, or CIP culverts, as they will be referred to. As you can see, the breakdown in here for the numbers, obviously 4-sided culverts are currently more common in the state. The numbers can vary. For example, the 4-sided cast in place are very limited. The 3-sided cast in place are very limited in presence. However, each category had sufficient number of culverts to perform the models. So the accuracy or the validity of the models may slightly differ, but we think that the number of culverts under each type is sufficient to perform that analysis. Now, after identifying the type of the types that we want to include in our analysis, we had to do some kind of data rearrangement. As I indicated, the tables compile all culverts into one master Excel table, and the inspection records were split by date, like so anything before 2009 were in one file, and then anything after that in another file. Our data rearrangement was very simple. We had to separate for each culvert a table, as shown here to the right, and transform the years of inspection into age. The data went all the way to 1985. So the age would be identified as the difference between the date of inspection and the construction or reconstruction for that sake. So if we have any reconstruction event, even inside the data here, we would reset the age to 0. Maybe that's not, there might be some other practices, but from our observation, that's a very reasonable assumption. Obviously, reconstruction, that means somewhat a new system may be placed in the same location, however, it's a new structure, so we've dealt that way with it. We had focused on the culvert summary data, which is a summary in condition index. The same concepts can apply to any condition index of interest, but that was the interest for this study specifically. All the processes obviously were done in using a simple code, a Visual Basic Code in Excel to facilitate the process. The next step was for us to diagnose the data. So data diagnosis, that's a very important aspect, and sometimes it can be overlooked. And I want to emphasize that it is very important to look at the data, because one of the problems with statistical modeling is sometimes using the wrong model can give you, by coincidence, high fit numbers, and you think that everything is beautiful and that it should be used. However, knowing the process and understanding the background of it is very critical. Knowing how the trend looks like, when the culverts will deteriorate faster, slower, how long would you expect that extent in each condition state be? Look also at some of the challenges, and we'll talk about that briefly. All of that can be seen by plotting multiple, random culverts you select from the database to look at how things would look like when you perform the analysis. So here are some of the challenges that we have identified in our database that comes from Ohio. And the same challenges, we've looked a little bit into the bridge database. There are very similar challenges. So one of the challenges, for example, is the brief drop or increase. Let's call it fluctuation in the data. So as you can see here, there is a fluctuation. So you cannot tell whether this was a sudden drop due to subjectivity, there was minor maintenance. These can vary, but also subjectivity, as I mentioned before, plays a major role. So for example, a culvert that has a lot of debris and all of that may have a lower rating in here. Then after a year, maybe these debris were gone due to some minor maintenance, or maybe naturally with the flow. And when the rater comes back or the inspector comes back, would look at it and say that maybe it deserves to go back to 7 instead of 6 being down here. The other challenge that we have faced is missing data, and that's all over the place for this data and other databases. And we'll talk about how we handled all of these separately. The last one I would say is, another important one is the construction date. In some cases, we didn't have any construction date. Such data can be used for certain models, but for our analysis, we excluded those because we had a large database that we can still build our models with. One thing I want to point out, and we'll talk about that in a second, is these challenges are relative to the type of model that you will be using. So for example, in our case, and here I will discuss the Markov model and survival analysis with Weibull distribution, knowing these models would dictate what is really a challenge and what is not a challenge and how this should be handled. So after identifying these challenges, we developed some kind of a workflow or project logic to describe the data pre-processing, how to handle these outliers or some of the issues that we have in the data. We had general guidelines that we've put and we've agreed on that we don't want to do data manipulation. I'll try to avoid that as much as possible. And the data pre-processing, as I mentioned, depend on the model. So some modifications are not necessary. So when you do these modifications, you're introducing bias into your model that maybe is not necessary, and you don't need to do that. And the final thing is to look at the data points that are in question relative to the other points in a string of condition data. For example, here for this culvert, you see there is a missing point in here, there is a missing point in here, and then there is a bump in the condition for brief 2 years and so on. So for the Markov model, simply we didn't do anything with that. And we'll talk about that specifically in our case that we have allowed in our Markov models for these fluctuations. For the Weibull model, on the other hand, we needed to identify a continuous period at which the culvert will stay in with a given condition state. So we needed to identify, is this one period where the culvert stayed in condition 8, or should we break it down? Obviously, breaking it down would also introduce bias because now you have shorter periods saying that the culvert stayed, for example, for 8 years in here and then jumped and then back 8 years. That wasn't very intuitive. So we've decided to look if it's minor improvement, for example, one condition rating, and for a short period of time, which is less than 50%, about, let's say, less than 40%, that was our threshold for 50%, then we'll just consider this as the minor improvement and fluctuation. However, this entire period is a period of condition rating 8. And also it depends on where does that happen. So if we, for example, these 2 points happen in here, we only have 2 points, these would be the drop, and this would be the full period. But since it's in the middle, so there is more points before it, and it's very short and brief, then it's considered as a fluctuation. Now, in general, after that, the logic of the deterioration model itself is very important as well. So deterioration modeling, if you look at it, we're trying to capture the degradation of the material. However, the actual degradation, engineering-wise or fundamentally, is happening at a continuous rate. So your concrete or relative continuous rate. Concrete is degrading, and you have cracks developing, and you have movements and settlements that are happening over time. However, when we perform the analysis, we're using the inspection records, which are discrete in nature, and also they have also discrete in time and discrete in condition scale. So we have a limited scale. We do not have actual crack width measurements or something like that that we can deal with. So the idea that there's an underlying continuous process is important to understand the limitation of the model that we're doing. However, it is also important to point out that the records that we're dealing with are the discrete records, that they have fluctuations as well. So all of that should be considered in the models. So going into a sophisticated continuous model or latent models solely is not always necessary, and it can be actually wrong in some cases, depending on how you approach it. Now, looking and searching in the literature and from our past experience, obviously, and we all know that Markov chain processes is one of the most commonly used modeling techniques for culverts and bridges, in general for discrete inspection records. So the basic concept of Markov chain processes, and there are different names out there: Markov chain processes, Markov models, Markovian models. Eventually, the original concept behind it was to look at particles. In our case, we're looking at culverts, and try to quantify or model the transitions from one condition state to another state. Originally, it was location, maybe, after one time step as probabilities. So P11 here to the left is the probability that that particle will stay and remain in its current condition state after one time step. P12 is the probability to transition to state 2, and so on. And as you can see, all the errors in here are going all over the place in different directions. So you have different possibilities. That condition state, or that particle, it can remain in its state, it can move to any other state, or it can even go backwards into other condition states. That was the original mathematical construction. However, for culverts, we would typically limit some of these transitions, and we'll talk about that in a second. So here we have the same concept, but now we're transitioning in condition space. So we want to see what is the probability that a culvert at a condition A, let's call it, or C at T1, state 1, will transition into condition 2 or 3, or it can remain actually in its current condition state after one time step. In our case, we're looking at after 1 year. All these probabilities are compiled into transition probability matrix, as you can see here to the left. The best condition state is 9, so the condition rating is different than these numbers. These refer to the state number. And to the left, we have the actual condition rating. So P11 is the probability that a culvert with condition rating 9 will stay in condition rating 9 after 1 year. And then all the way to 110 is the probability that same culvert with condition rating 9 will transition to the lowest condition rating, which is 0 in this case. So each row is, in some sense, some kind of a probability density function or probability mass function. I'm sorry for that sake, since it's discrete. So in here, as mentioned, we're looking at a transition matrix. This is an actual matrix for one of the culverts, or one type of the culverts. As you can see in here, we've limited the transitions at the first trial to either staying in the same condition or dropping one condition rating. And we'll talk about some other modifications that we have done. I wanted to point out that the total probabilities should add up to 1. That's intuitive, but it's important to know that each row is a probability mass function by itself. So the total probability is 1. Whether it's a known probability mass function or not, that's a different topic, and typically it's not very well defined, but the numbers are there, and it's not necessarily one of the commonly used probability mass functions. Now, some of the assumptions with transition probabilities when doing Markovian models, and these are not, by the way, always necessary, but that's what has been used because of ease and simplicity. The first assumption is homogeneity. So the assumption that these culverts transition, or the deterioration process is homogeneous over time, which means it doesn't depend on the time that you're doing the forecasting at. The only information that you need is the current condition state. When did that happen, or how long has it been in that condition state? That's not captured in the model. The other one that is memoryless, and there are some other assumptions, but these are some of the major limitations actually of Markovian models typically referred to, which means that the previous states, or the trend over time before the current condition state, is also irrelevant. So knowing that it has been, for example, 9 in condition rating 9 for 3 years and then transition to 8 for 4 years doesn't mean anything. The only thing that you need to know is the current condition state. So these are two of the major limitations with linear homogeneous Markovian models. These can be actually overcome by other assumptions, but it's not always done. Now, being a mirrorless or homogeneous transition system as well doesn't necessarily mean that we cannot look into the future with these. So to look at multiple steps, time steps from the current condition, you simply multiply the same transition probability matrix by itself. So for example, in here, we're looking at the transition probability matrix for the previous one after 5 time steps, 5 years. So if the culvert is currently in condition state 9 or has condition rating 9, after 5 years, there is a probability of 0.283 to stay in 9, and there is a probability of 0.608 to transition to 8, and so on. So if you look at the row in here, now it's a full probability best function with inputs in each column. Still, we have limited the transition back to an improved condition, except this, and I've left that on purpose because I want to catch your attention to that, and we'll talk about that. Now, the other important concept that I wanted to discuss with transition probability matrices is the expected value. So the expected condition rating after 5 years, for example, is simply the multiplication of each condition rating by the probability value and then summing these values. And for example, in here we have 8.1. Expected values do not mean the most probable observation, and they do not mean the what you should expect in the future. They only mean the centroid, or the center of mass of that distribution. In fact, it's a statistical measure. Now, in most cases, or in many cases, let's say, it will be the most probable observation. So in here, 8 has the highest probability, but that's simply because the distribution will have the mode close to the mean, which is the expected value. However, it does not mean that by essence, it only means the center of the distribution. And this is very important as well, because when we are trying to fit the transition probability matrix, what we're looking at, or we're looking for, is to minimize the difference between the expected value and the average rating. So if you look at the average rating in here, it's a continuous trend in some sense. We took the average for all culverts within each type. We had 4 types, remember. So we averaged, as function of age, we averaged the condition, which is the culvert summary in our case, and we've plotted these over the years. And you can see it's a continuous trend, which means that you will see a value of 8.5, you may see 8.6. You will not observe that for a single culvert, but you will observe that on average for a population or a group of culverts. This is a very important concept. And to really find the values for the probabilities here in the probability matrices, we simply, for each year, we multiply how many steps we're looking at, and we try to minimize the average at that age and the expected values by changing the transition probabilities. So by tweaking these transition probabilities for all times, you will end up with a transition probability matrix that best fit the expected, or the expected value of that would best fit the average trend that we're looking at. Now, if we use the limited setup that is typically used, where we only allow for the culverts to stay in the current condition or transition one condition state lower, you typically will end up with a rigid curve, and that's not always the case. Even in this study, we've tried it for different culverts. We had some flexible curves, some didn't have flexible curves, but the curve in red here is the expected value over time. And in many cases, it would be rigid, and that was reported as well in the literature. By rigid, I mean it's closer to a line rather than the curve that we see here in blue. And the one in blue is the actual average condition rating. And that, we thought, maybe that's due to the degrees of freedom. So if you look at the concept of degrees of freedom, is how flexible your model is. So allowing for more transitions means more flexibility in the model, higher degrees of freedom. So the number of arrows is not exactly equal to the degrees of freedom. There is a different definition for Markovian processes. However, in general, the concept, the more arrows you allow, the higher the degree of freedom that you have, and the more flexible your model would be. In our case, we have allowed for actually some extra transitions. For example, we've allowed two drops in condition states, and that happens. Sometimes the deterioration is accelerated, and over 1 year, it goes down 2 steps. We allowed also a backward transition where a culvert can be in condition state 7, it can go back to 8, it cannot obviously go back to condition states, but we observed that fluctuation between two condition states, for example. So what we did is to allow that in the model. We allowed in the fitting and the optimization, just allowed inputs, more inputs. One here, for example, is the off-diagonal element. And this zero, by the way, is the result of the optimization. It's not our enforced input. But we have allowed the algorithm to include more data in here. And we allow the algorithm to include more data in here. We didn't allow, however, culverts that reached condition state 5 to improve over time. Because from the data we observed that these are limited, very limited cases. Once it goes down to 5, it starts going down continuously. It doesn't go back. So this means higher degrees of freedom, more flexibility in the model. And it's more realistic. If you look at the data, that is what is happening. And we had significant improvement in the model fit. Our models could fit data better, looks better, and the statistics look better, and it makes more sense. Now, even with that improvement, we still have an issue. We do not account for the time in state. How long did the culvert stay in that state? We have no clue. It's not part of the Markov model. So our next attempt was to look at survival models, which is also common. It's not something totally new. People have done that before. So survival models, time in state models, sometimes simply called Weibull models, and we'll talk about that, why they are called Weibull models, are simply models looking at the probability that a group of culvert will remain a condition state for a certain period of time. For example, how long would it take before, let's say 20% or two culverts transition to state B? It's 8 years. And how long would it take to in total have 5 culverts in state B? That's 18 years. And now finally, and note the approximate sign in here, approximately 100% of the culverts would transition to state B after 26 years. So survival models are trying to quantify these probabilities. And you can see we've talked about multiple probabilities to transition from one state to the other over time. So what we're looking at is actually the time it takes and the probability for that time. So here's the mathematical construct, the basic concept of time and state models. We're trying to quantify the probability distribution for the time a culvert spends in a given state. So the random variable in here is the time, and what we're trying to quantify is the probability as a function of time. Now, the basic concept, and that has nothing to do with the actual distribution, which is the Weibull distribution in our case. It can be other distributions. There are 3 main functions: the hazard rate function, or lambda t, the survival function, S of t, and then the PDF, F of t, the probability density function. It can be also probability mass function, but it's typically looked at as a continuous model. I don't want to dive too deep into the mathematical construct to save time and touch on multiple topics. But in our case, and that was the practice, that is the practice, to look at Weibull distribution. The reason for it, it's a quite flexible distribution. It satisfies the relation between the probability function, the hazard function, and the survival function. And it is a special case of the more generalized gamma distribution, which is the most, I think, would be, or one of the most generic models out there that we can use. So it is a special case, but it's still quite generic. The exponential distribution falls actually under the Weibull distribution. It has a mean and a median, and the reason that sometimes you look at the median is that the density function is highly skewed, and we will see an example in a second. Now, when we perform the analysis, one of the most important challenges that we have is the censored and uncensored data concept. So as we use the same rearranged data and then went into each culvert and tried to identify the periods. So we are trying to find the time that culvert stayed with the condition state 8. Now, when you have uncensored data, you know the date that it started, or relative date. We're looking at years here, so the exact day is not as crucial. So we're looking, for example, in here, this culvert stayed for basically 4 years. Okay, I'm sorry, for 3 years with condition state 7. So this is uncensored data. We know for sure that it only stayed for 3 years. Can be a little bit more in here, 3.5, but we're just assuming that, 3 years in here. However, in some cases, we do not know when the culvert transitioned into that condition state. For example, all what we know here that it started at age 47. We have no clue if it was at 8 before that, for how long. Is it only 1 year before, or how many years? We don't know that. The same thing, we don't know how long it stayed after that, 58 years of age. So these are censored data. In this case, there are two types of censored, right censored and left censored. In our case in here, we only can say that this culvert stayed at least for these years. Okay, and here, for example, for 4 years. So the only thing that we can conclude that it was there at least for 4 years. Now, after extracting all of that, we rearranged. Now, we are not looking at the full record for individual culverts. We're looking at only trying to identify the periods they stayed in a given condition state. So, for example, here each number corresponds to a culvert in the database. So there's a culvert that stayed 6 years in condition 5. But this is censored, so it stayed at least 6 years. Uncensored data. So we have censored and uncensored, and each one would weigh into the analysis. If the censored data is overwhelming the uncensored data, your models will be biased, and you will not have very high confidence in the model. So the percentage of censored data is also important. We've attempted to go all the way to 60%, and I'm sorry, 76 even in here. But I would say some of these models can be a little biased. You would prefer something in the 30s, maybe, or even less. But that's the data that we have, and we try to make sense out of that data. Here's an example of the probability density function. This is a Weibull distribution, and this is how the PDF would look like. This is for staying in condition state 9. So we're looking at the for example, what is the probability that it will stay in condition state 9 for 20 years? Then you would just shade this area, and this area would be your probability. I wanted to point out that these distributions are continuous distributions. We're trying to fit the data, and it doesn't necessarily mean that your culverts will at some point stay for 60 years in condition state 9. It could happen. One thing, since we're talking about that, is the estimation and statistical analysis. Even though that you may have what we consider a population of culverts, you have all the culverts, but you don't have all possible culverts for all times. The only case where you have a full population that you have observed infinite number of culverts for infinite amount of time. So even if you have all the culverts included in the analysis, it is still considered a sample, because there might be a new culvert in the future that would remain in a given condition state for a much longer time. So eventually what we're trying to do here is to estimate the values. So with that, let me just talk a little bit more about the performance prediction and interpretation. Really quick here, the Markov models, as I mentioned, were developed to maximize the prediction of average performance and not the individual culvert's performance. So the interpretation of that is very important, because the way it was developed using the frequentist paradigm, and you can read more about the difference between frequentist paradigm and Bayesian paradigm. The frequentist paradigm is always concerned with a group of culverts or a group of observations, actually, and we're trying to assess the probability that on average things will move in a certain direction. And it doesn't mean that we're looking at the personal belief for an individual observation. For example, if you have an individual culvert, you cannot tell much about the probability that it will transition. But if we have a group of culverts, on average, our estimates would work out. Now, when you do the Bayesian paradigm for the analysis, you may end up with very similar numbers. However, the way that we interpret the data would be different. And there are other tools with the Bayesian analysis that would give you more insights into the performance of individual culverts. The other, or the third point, is basically how this should be used or could be used. It obviously can be used for life cycle cost analysis, estimating future expenditures, maintenance requirements, overall performance of the network. Now, if we have full Bayesian model, we can talk about individual culverts. But even if we don't have that, since we're talking about an overall performance for the network, things will eventually add up and work out. However, if we're concerned about individuals or individual culverts, the analysis should be a little different and improved. And it makes a difference at some point. Now, some of the alternative models and improvements possible is using non-homogeneous Markov models, and that's something out there. It's available. It's a little bit more computationally extensive, but we're looking into these models for future studies and papers. The transition probabilities, I wanted to point out, can be estimated from the time and state models, and people have been doing that. So this is some kind of a way around the homogeneous Markov model problem, where your probabilities come from the survival models and change over the years. Incorporating explanatory variables, that was something important. We could not because of the limited time of the project, but this can be very important and give more insights on how other variables, the surrounding environment and so on, would affect the condition over time. Updating and calibration tools to improve predictability of individual culverts. I talked about that a lot, and I cannot emphasize it enough that this is important. If you're looking at individual culverts, for example, if your estimation for individuals is wrong and your estimation for cost is wrong, multiply them, you will accumulate more errors at the network level. If we're looking at only the performance over time and we're not too concerned about optimization, for example, of costs, things being worked out. And also one thing that we didn't discuss, and I think others have been looking at it, it's not a new topic, obviously, the impact of maintenance and intervention activities in the model, how to construct that as part of the also model, and how it would affect the future deterioration and the models after these models. Now, in summary, I just wanted to wrap up this. If we look at it, we had a brief discussion about the culvert inspection process. We've talked a little bit about the performance data, and we've talked more about how to handle that data, use it in performance models, performance predictions, and we've talked about the interpretation throughout the discussion and a little bit more focused towards the end. We've discussed the limitations and alternatives, and we know that there is always a huge room for improvement for any study out there. So this is something that we're trying to improve and look at, even for this study, for future papers and publications. With that, I wrap up my presentation, and back to you, Jerry.
Yeah, thank you, Ahmad. And we hope you enjoyed today's presentation, everyone. A bit heavy on probabilistic and analysis and statistics for some of us. I'll be mentioning a little bit later that all of our webinars are recorded, and I'll tell you where you can access those if you're not already familiar with it. I'd like to tell you a little bit before we get into the Q&A period. And I do have a number of questions, and we still have time for you to submit questions if you haven't already. Upcoming webinars, register for those. Our ARA webinar series has been ongoing for over 3 years now. You see the registration address here. And then on April 27th, the next webinar will be Enhancing Design Through Value Engineering. And value engineering, of course, is not a new process being exposed in the infrastructure environment and engineering environment. We're going to hear some updates and experiences from Michael and Kenneth on April 27th. We also have, not listed here, we have presentations and specific presenters scheduled through July of this year. and our program will be continuing through the end of this year and beyond that. We typically go out about 3 times a year and solicit up the latest information in terms of offering of what ARA is working on. Having said that, all of our presenters are ARA employees, so this is all of the work that we do. Next slide, please. Now for a couple of Q&As, and Ahmad, like all of our presenters, has been gracious. Should we run out of time today and not be able to get to all the questions, or for that matter, if you think of a question subsequent to the webinar and you'd like to submit it, you see Ahmad's email address here. Please put it in the form of a general technical question and germane to the specific topic that we're speaking about today, and avoid as best you can and at all costs if possible. Asking a consulting question, that just simply wouldn't be the right thing to do. So with that, let me go through the questions that we received thus far. So Ahmad, the first question comes from Elizabeth, and excuse me, during your presentation, and I'll paraphrase some of these questions a bit, they're somewhat lengthy. During your presentation, you mentioned the use of deterioration models as applied to management systems. How would you use these models in a probabilistic sense in management systems? And second, related question, are there new techniques to incorporate this information and this technique specifically into asset management?
Sure. So generally that would follow the optimization process. So there are some already built up capabilities in optimization asset management systems where you can look at Monte Carlo simulations and scenario analysis. So using some of that probabilistic analysis, you can incorporate that in the optimization process. Also, one other thing is one output can be of the optimization process is the risk or uncertainty in the total performance and total costs and budgets. So that would be the best way. And there are obviously some tools out there already developed in the softwares out there and management systems and platforms.
Okay, well, thank you. Second question is from Sean. And Sean's question, and again, I'll paraphrase a bit. In your discussion on probabilistic models, you emphasized that these models are developed for the average condition of a population. And what differences would it make as compared to an alternative model, and what would be those alternative models? What might they be?
So I've talked a little bit about the Bayesian analysis. Bayesian analysis is not one model, it's a paradigm. And there is also a frequentist approach to that, where you can develop models for individual culverts. So when we're talking about the average, each culvert will have a bias from that average line. It's something similar to even other types of regression and statistical models, where you have an average line, however, none of the points are on the average line. So the only thing that you can tell that, okay, this is representative behavior, it's not necessarily the individual culvert behavior. Now, the difference it would make if you look at the cost, for example, and each time you have a bias and you account for additional budget and then lower budget for some of the culverts that will be actually shifted from that center line, your total budgets will eventually try to cancel out, but you may still have a high level of uncertainty in your budget estimates or maintenance schedules. Especially for maintenance schedules, you're trying to capture which culverts or which assets, for that sake, you're trying to maintain or put in line for the next round of maintenance. If you have that uncertainty, your assumptions may be wrong, and you may end up flipping these numbers each year and re-look at it or look at it again. And that actually happens with many DOTs, and that's why even though some of these deterioration models are developed for years, some DOTs or agencies only look at, for example, a year ahead. For the overall performance, you look at 5, 10 years long-range planning. But for more specific plans for individual maintenance actions or programs, you may look only for 1 year or 2 years. That's it, because you cannot look at a very long range.
Okay. That was a long answer to a long question, so that's very good. I have currently one more question, and I want to repeat again. This is a pretty heavy discussion technically today, and takes you a while sometimes, individual participants, to formulate thoughts. So again, Ahmad will entertain questions for the next 48 hours on this topic, and I can attest to that. As an example, I gave a webinar 2 weeks ago, and I'm still getting emails from people that looked at the webinar 2 weeks ago, so they've just got their questions 2 weeks later. At any rate, the next question comes from Hassan, and question is, as you pointed out, the assumptions in the Markov model sound counterintuitive, dependent on the tree of the asset. How can you still use that model, and could you expand a bit more on non-homogeneous model?
All right, so one thing with statistical models, sometimes the mathematical assumptions do not sound right. However, they reflect the actual behavior. And if you look at the survival models, not only for this, for example, the exponential models and exponential distributions, they all have that memoryless behavior. Does it really mean that the culvert is not affected by the past history? That's not true. However, there's something that we do not understand underlying the process, and our model is fitting that. So I want to give a little bit more specific example. With probabilistic analysis, there's the assumption that things are uncertain or has randomness built into them. However, if you look at the fundamentals, probably many of these systems are in essence deterministic, but they are too sophisticated and they have too many variables that interact with each other that we cannot describe. And typically these are referred to as chaotic systems, where you may know how one particle would behave or one specific point in a culvert would behave over time, but you cannot tell for the entire culvert, and things get too messy at some point that you cannot model them. So using these distributions eventually works out. So that's the answer for the first part. And the second part was, I'm sorry, can you repeat the second portion of the question?
Yeah, the second portion of the question was, how can you still use that model? And can you expand a little bit further on the non-homogeneous model?
Yes, so I think, using that, as I mentioned, it's behaving well and it's capturing the data. And using that non-homogeneous or non-homogeneous assumption, the assumption is basically that your process does not change over time. So if you take cross sections, everything will, in a probabilistic sense, remain the same over time. The way that things behave over time does not change.
Okay. And we do have another question that recently came in. This is pretty straightforward. John asked if you would please explain the difference between a 3 and a 4-sided culvert.
Sure. So the 4-sided culverts that would have a floor and then basically 2 sides and a top. Some of the 3-sided culverts would have maybe stabilized base and so on, but it's not structurally part of the closed 4-sided loop of the culvert. Okay,
very good. I would also add, and we don't have any further questions, but I would also add that this topic is an emerging topic across the board, even in terms of infrastructure features such as pavements and bridges, where we have a lot of historical data, but we haven't really fully developed the ability to make predictions relative to rates of deterioration, or for that matter, what the deterioration models are. So for example, quickly, if you build a new highway tunnel today in the United States, it has a service life that's commanded of 150 years. Well, how in the world do you even evaluate that at an initial design stage, let alone while it's in service? So just thought I'd whet your appetite that you're going to see a lot more of this as we go forward. Next slide, please. So just a few more items to share with you. First of all, on behalf of ARA, I want to thank you all for joining today. As I mentioned previously, today's presentation is recorded, and as we usually do, a link will be made available at the ARA Webinar Wednesday website, probably in about a week. We'll also send and make available a PPH certificate to all the participants who verified by our attendance log that participated in the entire hour. And finally, along those same lines, a PDF copy of the presentation will also be included. Please allow a couple of weeks for the certificate and the availability of that information. Next slide, please. Well, and then this is the final slide. So I want to thank you personally for joining Ahmad and myself today again. ARA is a fantastic company. We're a national firm, and we're always looking for great people. And we strive to hire valuable colleagues who are interested in science and engineering, have the right skills, and also who can demonstrate our core values, our passion, freedom, service, and growth. So currently in an ongoing process, we have a number of opportunities. If you're interested in the current employment opportunities, you read along with me, particularly for ARA's business sector that deals with transportation and infrastructure. That's where both Ahmad and myself work from. Please send a brief resume and send your contact information to the address that you see here. So have a great day. Thank you once again, and God bless you all. We'll see you next month, April 27th. Don't forget. Take care.